All right, another week. Time for another question show. My wife is traveling to Costa Rica. She's going to be taking her fancy camera away. So this is going to be the last episode for a couple of weeks. And I'm going to be able to use this setup. And then, so prepare for some experiments while she's gone. Production quality will absolutely go down. I warn you in advance. But one thing that I've just created, which you should totally check out, is I've got a new weekly newsletter, which sort of has just like a whole bunch of space news, stuff that we're writing on Universe Today, just stuff that caught my eye, stuff that I think you're going to dig, that I don't have any other place to put. So if you're interested in that, I'm going to put a link as a card to Universe Today. Go to universetoday.com/newsletter and you can sign up once a week. I promise you it's going to be exactly what you want. So check it out. All right, let's get on to the questions. Larry Johnson. Fraser, ever seen an Iridium Flare? I never heard of them until I got an app that helps me find ISS on the night sky. Pretty cool stuff. I've seen probably one Iridium Flare, and totally by accident. But I knew what I was seeing. So if you don't know, the Iridium constellation are a bunch of satellites. They're used for internet and phone calls kind of globally. And the cool thing about them is they have sort of one surface that's very, very reflective, and you can predict when you're going to see one of these facets of these satellites sort of hit the sunlight perfectly from your location on Earth, and you'll see this flare come out of nowhere. And I probably get an email once every 2 weeks or so where someone says, I just saw this really bright flash. What did I see? What was that? That was an Iridium Flare. So the good news is you can go to a website like Heavens Above, and there's other places. Do a search for Iridium spotting or Iridium flares and tell you when you're going to be able to see an Iridium flare from your location on Earth. The bad news is that these satellites are eventually going to be deorbited. It's going to happen fairly soon in the next few years. So this unique opportunity to see this really cool flash in the sky is going to be going away over the next couple of years. Our intro. My questions have to do with interferometry as used in astronomy, so that two or more smaller telescopes are used to get the effective resolving power of a much larger telescope. Radio telescopes have a much easier time using this technique than optical or X-ray telescopes. How come? So the process of interferometry, as you said, is that you have two telescopes that are separated by distance. And if you can get them synchronized, then you get the equivalent of a telescope with the size of the distance between those two telescopes. Now you don't get the resolution, but you get the aperture, you get the size of the telescope, which is very, very useful. And the vast majority of the time this is used for radio telescopes. There are a couple of visible light interferometers out there. There's one in Chile, in some of the very large array, I believe. But there are visible light telescopes in Chile that are used for interferometry. And the reason that it's easier to do this with radio telescopes and not visible light is that you have to get the wavelength perfectly matched up. Like, you know, when you think about radio waves, let's say a radio wave has a very long wavelength, like in the centimeters, right? You might have a wavelength of radio waves that's like this long, right? Big, long radio waves. And so if you've got a really accurate time clock, you can synchronize those two radio waves coming in from those two observatories perfectly. But if you've got a visible light telescope and it's got, say, 400 nanometers, right, to get the two wavelengths perfectly lined up so that they're essentially showing the exact same moments of light is incredibly difficult. And you can only really do this with two telescopes, and you line them perfectly and you get them perfectly lined, set up so that you can do this. But with radio telescopes, you can actually do this after the fact. So you can set one radio telescope pointing at a target, and then one that's half a world away pointing at the same target. You can then download the data files and you can then synchronize them after the fact. But you can't do that after the fact with visible light telescopes. Now, one of the really cool ideas is this idea of putting interferometry in space, because in space you can precisely move your spacecraft closer and farther from each other until they're perfectly aligned and the wavelengths are matched up. And then you can have this interferometry in space. And this is one of the space missions that was canceled, and the terrestrial planet finder would be using this idea of interferometry. So I really hope that it comes back and that we test more and more ideas about interferometry. But this is why you can't, say, connect together all of the amateur telescopes on Earth to act like one big telescope the size of the Earth, because you can't get the wavelengths perfectly lined up in the way that you can with a radio telescope. Valentine Parks. Fraser, if gravity causes time to slow down, especially high gravitation fields, then where would time flow the absolute fastest? Where would it be measurably faster? So for the purposes of time dilation, let's talk about the two effects that are going on, right? Like the one is when you're in a gravity field, and we saw this with the movie Interstellar. When they were close to the supermassive black hole, time moved differently for them. So they experienced what felt like a day, and the rest of the universe experienced, was it 40 years or something like that? So obviously for you to experience the least amount of time dilation, you're going to want to get as far away as possible from any kind of void, any kind of gravity. So the places that those are going to be is going to be in the supervoids in the middle of galaxy clusters, far, far away from all these galaxy clusters. That's going to be the places you're going to experience the least amount of time dilation. But the other kind of time dilation that you can experience is the one of moving relative to some other object. And the thing with that is that it's all relative. So if you're in one of those supervoids and the universe is expanding away and you're really far away from me, then maybe you're going to experience some time dilation compared to me than if we're very close. And so in that case, to experience the least amount of time dilation, you want to be as close and moving the same speed as the person who you want to be experiencing the least amount of time dilation. Really, it's not even about close. It's just about this. It's just about the speed relative to somebody else. Now, one thing that's really interesting, and we talked about this in an episode a long time ago, is that based on sort of the expansion of the universe, there's about 30,000 years of time dilation depending on where you are because of the speed of the expansion of the universe. And so even what we think of as time isn't the same for all parts of the universe. It's a very mind-bending idea. Mr. Man Buzz, probably a stupid question, but how do you drill into something that is multiple kilometers thick? This was a response to the Europa Ice Sea Worlds episode that we did. And so, yeah, you're right. That, it could be that Europa has tens of kilometers thick of ice. How do you get down there? Yeah, we have a hard enough time drilling through that amount of ice here on Earth. How do we do it on Europa? And the answer is that probably we can't, right? That if it is 100 kilometers down, we would be hard pressed to get that deep here on Earth. In Antarctica, some Russian drillers have gotten down, I think, about 10 kilometers, but to go 100 kilometers, that's going to be really tough. So some of the cool ideas that I've seen, though, is, for example, you take a nuclear reactor, like a RTG, in some kind of torpedo-shaped drill, and so it gets really hot, and then you just let it land on the surface of Europa, and then it just melts its way down, and it sort of spools up some kind of communications cable behind it. And when it finally reaches the under ice ocean, its end opens up, and some little spacecraft, little probe, a little submarine pops out and zips around underneath the ocean and communicates its findings back to the tether that takes back up to the surface and communicates what it's seeing back to the rest of the world. But one of the ideas with the Europa Clipper mission is that it's going to have this ice penetrating radar, and it's going to be searching for pockets of water that might be very close to the surface. And so then future missions, if they want to drill, will go there instead of just some random spot on Europa. Jack. Couldn't they set up a way to deliver a fuel payload to the James Webb Space Telescope? In theory, yes, right? It's out in space. They're developing the SLS rocket, the Orion crew capsule. There are other options out there. So maybe they could get a mission out to James Webb and bolt onto it and try to sort of keep it going for a longer period of time. And it's not that NASA didn't think of this. They actually have attached a docking rim, or sort of like a docking ring, to the James Webb Space Telescope. So if some future mission does make it out there, it will be able to, with the right specifications, be able to clamp on to James Webb and then be able to boost it and keep it going and extend its operations for longer. But when you think about if the SLS costs billions and billions of dollars to launch and the James Webb costs $7 billion to launch, it might just not be worth it. Instead, just launch another space telescope if James Webb finally fails after 10 years. Scott Gibson. The Pentagon suggests you may be mistaken about there being non-evidence of alien life in any event. Nice video, thanks. Yeah, after this round of videos came out from the Pentagon, I got a bunch of people saying, well, what do you think now? Do you believe in aliens now? I'm like, no, I don't believe in aliens, in that UFOs are aliens. the problem is that it's eyewitness testimony, it's people seeing things, and for me, we all get to make our own decisions about this, right? And so if I say that I saw something really strange, but you didn't see it, and there's no way for you to confirm that it's there, then you really just have my word for it. It's just my personal testimony. And so, unfortunately, I can't take personal testimony as evidence. Do I think that the Pentagon found evidence of unidentified things flying in the air, objects maybe? Yeah, it looks like it. It doesn't surprise me that the Pentagon is trying to collect information about perhaps what kind of secret aircraft some of their, some other nations are working on, and they're going to be trying to watch out for them. Maybe there's some technology that they can take advantage of. But until there's some kind of corroborating evidence, it has to be unidentified, right? Unidentified flying object does not mean aliens. So I didn't see anything in the stuff that the Pentagon released that said, oh, it's aliens, right? In that it's got, they're using metals that can't be explained by anything on Earth, or, one of them landed and crews went inside and took pictures and interviewed the aliens, right? Like, it's just, right now, it's still just eyewitness evidence, and it's not enough to convince me that it's aliens. So, unidentified flying objects, and I still the same thing as the last video that I did. But I just want to say, like, if that amount of evidence convinces you, that's awesome, right? Like, we are entitled to have different amounts of evidence, have different levels of what it takes for us to be convinced by evidence. So if that evidence convinces you, awesome. It doesn't convince me. And if you want to convince me that it's enough evidence, but really until, I can hold the alien spanner wrench in my hand, or shake their hand, or get photographs of their home world, like that's the kind of evidence that I'm going to need to be convinced. And until then, I'm happy to just go, I don't know, it's unidentified. Mad Gamer: does gravity flow like waves? I don't know, but if it doesn't mean that it would have the same speed, which means that if a star is pulling something from far and that star is like 100 light years, that star suddenly vanishes, the object will feel the pull for some time, right? Thanks to the kilonova explosion, this collision between two neutron stars earlier this year, where we detected both the gravitational waves and the visible light from this explosion, we know that gravity moves at the speed of light. And that means that, yes, indeed, if the sun disappeared, the Earth wouldn't know that the sun was gone for about 8 minutes. And so the Earth would continue to be orbiting the missing sun, the gravity of that the sun had emanated 8.5 minutes ago, and then 8.5 minutes later, when the gravity catches up, the Earth will then zip off into space, no longer being in orbit around the sun. It's an amazing discovery, and although, we actually did a video several years ago about it, and it was like, astronomers are pretty sure that the speed of gravity is the speed of light. Now we know 100% certain, which is awesome. Period. Since the surface of Europa gets refreshed so often from below, if there's life in Europa's oceans, dead, frozen things should be in the surface ice. Take a microscope with your probe and examine the ice closely. Yeah, it gets even better than that, right? But absolutely, that if you've got the surface of Europa is so fresh that it means that some kind of ice, something is constantly resurfacing the ocean, resurfacing the surface of Europa. And so water is sort of welling up in cracks and is spreading out across the surface and resurfacing the world. And absolutely, you're going to want to send a lander to one of these points, wherever these are, where this resurfacing is originating, and you're going to want to examine with a microscope what's in the ice to see what's down there, maybe. The other thing, though, it makes it even easier, is that these worlds, Enceladus and Europa, have geysers that are spraying material out into space. So it's not even just ice material that was emanated, say, hundreds, millions, billions of years ago, but actually material that was water just moments ago, right? And now is being sprayed out into space. And so fly a spacecraft through these plumes and sense what's in this material, and you may get a sense, you may be able to detect some kind of biological either life forms or the chemicals that are given off by them. It's really an enormous discovery that these things are there, and it's like someone left just this great clue, right? There's just this real easy way for us to be able to go and find out more. Solutrean cuisine. Was the sun smaller but hotter at one time? The sun was smaller and cooler in the past. And this is one of the thoughts about why perhaps Venus was more habitable in the past, although Mars was maybe more habitable too. But the thing that's going on right now is that in the core of the sun, you've got hydrogen being turned into helium. And that helium isn't just being destroyed, it's sticking around, and it's sort of adding to the amount of heat that's coming out of the core of the sun. The core of the sun is actually expanding a little bit inside the sun, and that's sort of increasing the overall heat that's coming out of the sun. And so over about the next 500 million to a billion years, the temperature on Earth is going to increase to the point that actually life on Earth is no longer viable. It's going to take about a billion years, and then the oceans will boil away, and then the solar wind will knock the hydrogen out of the atmosphere, and will be like Venus, although maybe not the same kind of atmospheric density. So when the sun has whatever it has, another 7 billion years to go, actually life on Earth on the surface really only has about a billion years left. Gertinos. Why does NASA want to send a probe to Titan and not Europa or Enceladus? Well, NASA is sending a probe to Europa, right? The Europa Clipper, and that's coming up very soon. And then sort of the next idea for a Discovery class mission is going to be this mission to Titan, Titan helicopter, or maybe it's going to be a mission to go back to the comet that Rosetta is at. In planetary exploration, there's sort of these stages that they do. The first thing they do is they send a flyby. And a good example of a place that's only had its first flyby is New Horizons flying past Pluto. The next thing they do is they send an orbiter. And so a good example of an orbiter is, say, what Cassini was doing at Saturn. This was after the Pioneer had gone past Saturn, after the Voyagers had gone past Saturn, they'd done their flybys, and now you send Cassini, which is an orbiter that sticks around and does a lot of science. The next thing you do is you send some kind of lander, right? We're seeing this kind of thing on Mars. We saw this on Venus. We see this on the Moon. And then the next thing you do is you send a rover that can actually move around and do more science on the go. And it's sort of these stages that they go through as they're exploring the universe better and better. And so we've gotten past the flyby stage of Europa, and now it's time to move to the orbiter stage of Europa with the Clipper. Although the Clipper isn't exactly going to be orbiting Europa, but still, it's going to essentially be functioning like an orbiter of Europa. So it's on two different fronts. The next stage after the orbiter for Europa is going to be probably some kind of lander, and then maybe some kind of rover or submarine or something. And we're going to see that same progression happen over on Titan. Michael Alexander. Why do we endlessly search for the smallest bit of life? Why don't we conclude that life exists everywhere, but only the highest forms of life are worthwhile? Why do we spend trillions to get a microscope image of living material? If Fermi is true, life is everywhere, and blocking out those not worthy will allow us to achieve supreme existence. We're curious. We want to know what is the story of life. And to understand the story of life on Earth, we want to understand, is this the way life always evolves, or is it that life evolves differently on different planets? If we go to Mars and we do discover some kind of microscopic life there, will it have a completely different source of the way that it operates? We don't know. This is a question. This is what science is about. But to say that they're spending trillions, it's not trillions. I mean, the entire budget of NASA is what, $20 billion US a year? Think about how much is spent on military, right? You don't think it's more important to find out maybe how life works? I guess possibly the most important question that we can ask, right? How did we get here? How are we different? Is there life in the universe? And I don't want to just make any assumptions. I want to go and look. I want to find out the answers. I'm curious and I want to see how it all turns out. So I think that it's totally worth spending a fraction of the military budget to spend in trying to understand what I think is the most important question we can ask. Ashlyn Murphy. If the black hole is at the heart of the Milky Way, wouldn't it be hidden in the zone of avoidance? How do we know the orbits of the stars around it? The zone of avoidance is actually a fairly old term, and this was back in the day. There's this big cloud of gas and dust that obscured the center of the Milky Way, and it was this place where astronomers really couldn't see behind it and see behind the Milky Way. But over the last few decades, they've gotten better and better with different wavelengths of light. And the one that's really good at penetrating through this gas and dust is infrared astronomy. And so in the olden days, the zone of avoidance was this huge area that they just couldn't see behind and made the great attractor this big mystery. But now, using infrared astronomy, you can actually see right to the center of the Milky Way and even to what's going on the other side of it. And the thing that they can actually see in infrared is they can see these stars moving like comets around this missing invisible thing at the middle of the galaxy. And that's how they're able to calculate the orbits of these comets and use that to determine the mass of the object that's in the middle of the Milky Way. And now, using radio astronomy, this year the Event Horizon telescope is going to be producing a photograph of the event horizon around this supermassive black hole. So the technology has just gotten a lot better. All right, another week, another question show. Thanks everyone who sent in their questions. Thanks to the patrons. I answered 3 of your questions at the beginning, and then thanks to everybody else who asked their questions in the comments. Remember, wherever you are on my channel, if you have a question, just type it in and I will gather them all up and answer them here. See you next week.